So hello everyone, this is the problem solving session of the course Matrix Analysis with Applications. I am Pawan Kumar Raikwadi, PMRFTA. In this session, I will explain some sample problems that will explain you or that will guide you in understanding the concept more and solving the assignments by your own. Okay, so let's get started. So question number 1, we have that A, B, the 3 cross 3 real idempotent matrix, that is A square is A. If A is non-singular, then what is the trace? Okay, Ajay, I think has solved the problem. Can you explain how do you reach the answer?
Sir, for idempotent matrix, we have 0 and 1
Hmm.
eigenvalues,
Yeah.
and so a matrix is non-singular, so 0 can't be the eigenvalue.
Mm-hmm.
So the 3 cross 3 matrix eigenvalues will be 1 or
Yeah.
minus 1, maybe.
No, no, no. I think maybe I misheard you. The total number of the number of eigenvalues of any 3 cross 3 matrix will be 3. You will have kind of 3 eigenvalues with including algebraic multiplicity. And for idempotent matrices, eigenvalues can be 0 or 1. These are the only choices of eigenvalues, right? Now, if the matrix is non-singular, A is non-singular, implies 0 is not an eigenvalue. Means what are the eigenvalues of A? 1, 1, 1. These three are the eigenvalues of A. And what is the trace? Trace of any matrix is the sum of all eigenvalues, which will be 1 plus 1 plus 1. It's 3. The answer is 3. Is it clear now?
Yes, sir.
Let's go for the and I hope everyone has an idea why an idempotent matrix has only eigenvalues at 0 or 1. Is it explained in the course?
What are you saying, sir?
Why an idempotent matrix has only eigenvalues 0 or 1? Is this explained in the course?
Yes, sir.
Yes, sir.
Okay. Okay. Let's go ahead on question number 2. That A is this matrix and we have asked what is the range of eigenvalues, modulus of that range. So we'll use the Grish-Gorin's theorem here.
Sir, D option.
Uh, Let me calculate. So by Grish-Gorin's theorem, the maximum eigenvalue we have to choose mod lambda will always be less equal minimum of you take the row sums and then column sums. Okay, how do you write it? Minimum of okay,
Sir, is it minimum or maximum?
like minimum of maximum of row sums, comma maximum of column sums. Okay, I mean I'm writing a combined statement. I think the only Grish-Gorin's theorem is that the eigenvalue cannot exceed the maximum of the row sums, right? That's the one that explained in the class.
Yes, sir.
Yeah, but now you apply the same theorem on A transpose because I set of all eigenvalues of A and A transpose are the same, right?
Yes, sir.
Hence, it cannot exceed maximum of row sums as well as maximum of column sums. That means it cannot exceed the minimum of those. So, what is your maximum of row sums? The first row sum is 5. Second row sum is 2 plus 4. This is 6. The maximum row sum is 6. Then what is maximum column sum? That is 5. This is 4, and this is 6. Again 6, so the minimum is 6. Okay, I think the answer is option number D. Okay, is it correct? Do you have any doubts?
Yes, sir.
Well, explain why I choose this combined statement. I'll just explain in one sentence. So, original Girish-Gorin's theorem states that for any matrix A, its modulus, its eigenvalue cannot exceed the maximum of its row sum. Also, since A and A transpose have same set of eigenvalues, we get equation. I'll call this as star. Okay. First question number 2. Simple application of Gresham-Corin's theorem applied to A and A transpose. Which of the following can be a set of eigenvalues of a skew symmetric matrix of order 3 cross 3? Okay. So a skew symmetric matrix simply means that A transpose is same as minus A. Okay. And what the possible
C
what are the
option.
possible eigenvalues? What you're saying? Option number C.
Yes,
Okay. Why?
sir. Because skew symmetric matrix has eigenvalues are purely imaginary or
Yeah. Then C does not have purely imaginary eigenvalues. No? C has the real eigenvalues.
real eigenvalues, sir.
You are saying skew symmetric matrix have purely imaginary eigenvalues. Yeah, Vindhya, please tell what's your doubt. You have raised a hand.
Sir, option B.
Yes. Option B is the correct one. Can you explain how?
Sir, because the eigenvalues of skew symmetric matrix are either zero or purely imaginary.
Yeah, okay. That's true. Okay. So do you know the proof of that statement? Or sir explain the proof in the course?
Yes,
Sir,
sir.
explain in the course, sir.
Okay, explain. Then fine. Then for question number 3, you have option number B. Because eigenvalues are either zero or purely imaginary. Okay, let's go ahead for question number 4. Consider the inner product on P2, the set of all polynomials of degree at most 2 over the field of reals. Okay, this is the inner product we got, that inner product Fg is integral of their pointwise product. Okay, then they asked us to find this inner product. Okay, it's simple calculation. Integral 0 to 1, the product. Jeez. Mm, sorry for that. Ah, so yeah, this is 2t squared minus t plus 2t minus 1 dt. Integral is 2t cubed by 3, then this is plus t, this integral is t squared by 2 minus t. 2 by 3 plus 1 by 2 minus 1. The answer is 1 by 2. Option number C. So this was just a basic calculation. Nothing else. Okay, so question number 5. Let W be the subspace of R3 over R spanned by S, then the equivalent orthogonal basis for W is. Yeah, okay, that's the question. So you have W which is spanned by these three vectors. Now we want to find an equivalent orthogonal basis. Does anyone have any idea how to find?
By finding orthonormal basis.
Yeah, that's true. But how do you do that? By using Gram-Schmidt, right?
Yes, sir.
Yeah. Okay, I'll explain a bit about Gram-Schmidt method. Um, the formula everyone knows, like if you have set of all vectors u1, u2 until un, then what you do is you take first vector maybe as wn, which is u1 by norm u1, that is your first vector of an orthonormal basis. Then you take v2 as u2 minus inner product of u2 with w1, say, then w1, and then go on, right? And then sorry, w2 you write by v2 upon norm v2. This is your second vector, W2. This was your first vector. Similarly, you go on ahead, and then you get your n orthonormal, an orthonormal basis with span same as of this span, right? This is the standard Gram-Schmidt procedure, right? Gram-Schmidt, just Gram-Schmidt procedure. I will try to explain just why this method gives you what you want. Let's suppose W I'll call a span of two vectors, simply U1 and U2. Right? I don't know about these two, U1 and U2, whether they're orthogonal or not. Right? I want to find a kind of V1 and V2. Yes, Suraj Pathak, do you have a question? Okay. So I want to find V1 and V2 such that the set V1 comma V2 is orthogonal and W, I mean the span is same as span of V1 comma V2. Okay. So how can I do it? The natural way to ask is let's fix V1 as your first vector, V1. I don't care about the orthonormality right now because for that you just have to divide by norm, then it becomes orthonormal. No need. Yeah, I fix V1 as U1. I want to find something in place of U2, in place of U2, such that inner product of that new vector V2 with this V1 has to be 0. Okay. What if I put V2 as U2 minus some alpha times what do you say, U1? Okay. If I put this new vector V2 as U2 minus some alpha times V1, does span of U1 U2 is same as span of this newly constructed V1 V2. Among those, V1 is same as U1 and V2 is this guy. Is it span? Is it same? The answer is yes. How I'll prove this? See, span of U1 comma U2. Basically the linear combinations alpha U1 plus alpha 1 U1 plus alpha 2 U2 for all alpha 1 comma alpha 2 belongs to R. This is the span. Now let an element belong to this span of U1 comma U2, that what I call just U. U is an element in span U1 comma U2. That means there exists some maybe alpha 1 and alpha 2 such that you can you can write this U element as alpha 1. Suraj, you started presenting.
Sir, your screen is not visible.
Yeah, just a minute, just a minute. By mistake, one of the candidates started their presentation. Yeah, now is it visible?
Yes, sir.
Okay. So now you can write that U as linear combination of U1 and U2. Okay. The question is, can I write this U as linear combination of V1 and V2? So I want to find kind of new vectors beta 1, beta 2 such that U equals to beta 1 V1 plus beta 2 V2. Just give me a minute. Okay. So let's equate alpha 1 U1 plus alpha 2 U2 has to be same as now beta 1 V1 is again U1 and V2 is as we claimed U2 minus some alpha times U1, right? Yeah. That means what is the coefficient of U1? I'll get as beta 1 minus alpha times U1 plus beta 2 U2. So by comparing, I will fix beta 2 as alpha 2 and alpha 1 will be then same as beta 1 minus alpha, that is beta 1 equals to alpha 1 minus alpha, right? So for any choice of alpha 1, alpha 2, you can find beta 1 and beta 2 because alpha is known to you, alpha 1 is known to you, alpha 2 is known to you. You can find beta 1 and beta 2 such that u is now same as beta 1 v1 plus beta 2 v2. The point that I want to say is for any alpha that you choose, span of u1 u2 is same as span of v1 v2. Okay. So now the only thing that you have to want to add is inner product of v2 with v1 also has to be 0. For that we need a special alpha. So what is that alpha? It needs inner product of v2 with v1 at 0. So what is inner product of v2 with v1? v2 was u2 minus some alpha times u1. v1 is u1 equals to inner product of u2 with u1 minus alpha times inner product of u1 with u1 is 0, which implies alpha as inner product of u2 u1 upon. So this is the alpha that you want to choose. That's how you do the Gram-Schmidt procedure. Now you remember what is my v2, u2 minus this alpha. Inner product of u2 with u1 divided by inner product of u1 with u1 times u1. See, in the standard Gram-Schmidt procedure, you name this vector as your w1 or v1, whatever it is, and then you find the second vector in this method, right? u2 minus inner product of that vector with this w1. Okay, so that's how this works. Okay, do you understand the whole concept of this Gram-Schmidt?
Yes, sir.
Okay, so now this is just a standard thing to do calculation. You have the first vector as 301. Equivalent orthogonal basis, you want to find the second vector. v2 will be u2, that is minus 107 minus inner product of minus 1, 0, 7 with the first vector 3, 0, 4 divided by the norm of the first vector. I'll just start inner product, not norm. And the second the vector. This value is minus 3 plus 28. This value is 9 plus 16, 304. Yeah. So this is 28 minus 325 upon 16 plus 9 again 25. This is 1. This is 304. 3 minus 1, 2, 0, 3. Oh, sorry, this is minus 1. Minus 1 minus 3. This is minus 4. Minus 403. So you are in either for second or number 4. Okay. So either you can calculate directly or you can just simply check the third vector has to be orthogonal with other two. Is this orthogonal with the first one? What is the inner product? 3, 3, 9 and then minus 28, not 0. So this is gone. This is the right option. Okay. I hope this is clear. Question number 5.
Yes, sir.
Let's go ahead with question number 6. Consider the set W as set 1, 1, 0 transpose, 0, 2, 1 transpose, 4, 2, minus 1 transpose, and the vector ABC of R3 will be orthogonal to W if. So you want ABC to be orthogonal with every element in this spanning set. This has to be 0. By this you will get a condition as A plus B has to be 0. Then you equate the inner product with the second element. It has to be 0. By this you get the condition as 2B plus C is 0. And you do the same with the third vector. By this you get 4A plus 2B minus C at 0. This is equation number 3. So how do you boil down these three conditions to just two conditions? Simple. The most simple thing is matrix, or simply just add these two. Let's see what happens. If I add these two, I get 4A plus 4B is 0. That is A plus B 0, which is again the first condition. A plus B has to be 0. Okay, let's just make matrix. 1, 1, 0, then 0, 2, 1, 4, 2, minus 1. Let's do some row transformation. R3 changes to R3 minus 4R1. So here we get 0. 2 minus 4 is minus 2, then minus 1. Then when you add the last two will become 0. So the only essential conditions are A plus B at 0 and 2 times B plus C at 0. A plus B 0 and 2B plus C 0. Do you have any such condition? Yeah, so you have to really check. A plus B is equal to 0 is a condition. The second condition you have is 2B plus C 0. What that means? That means C is equals to minus 2B. And from here you get B is equals to minus A. That means C is equals to minus 2 times minus A, which is 2A. Right? That is again 2A minus C is 0. So another form of the same condition is that A plus B is 0 and 2A minus C is 0, which is option number D. Okay. basically how do you check is to find the relationships between A and B instead of equations. How can you represent all the variables in some variables? For instance, the exact representation is A has to be anything, then B will be minus A and C will be 2 times A. This is kind of a parameterized form of the solution that you get in only option number B. In option number C, what do you get? B equals to minus A and C is equal to minus B, which is again A. Right? This is not the correct parameterization that we have. This option number 2 is the correct one. Then question number 7. If x is 2, 1, minus 1, y at 0, 4, minus 2. What is norm 2 squared of y plus norm infinity of x? In calculation, square root of summation of entries 0, 16 plus 4. Okay, we have squared, no square root. It's 20. And what is norm x infinity? It is maximum of modulus of xi's, where I runs from 1 to n.
22.
Yeah, modulus of xi is 2. The answer is 22, correct. Then we'll go for question number 8. We get v1, v2 and v3 if the vectors u, w are such that input uw is 0, then the value of a is. Okay. So what you have is inner product of a, not u, a v1 plus v2 and v1 plus v2 plus v3 is 0. What is this vector? Summation of these three. You get 3 and 0, 1. And a v1 plus v2, what do you get? A and minus a, 1. This has to be 0. Simply 3 times a plus 1 is 0, which implies a equals to minus 1 by 3. So these questions today are mostly all kind of calculative. I didn't notice this. There's no much mathematics involved. Question number 9. A is given a matrix, then the E norm of A. Yeah, the E norm of A is simply square root of trace of the matrix A transpose A. So you just have to find A transpose A, multiply, find the A transpose, then multiply, and then sum up the diagonal entries. That will be your norm AE squared. As far as I remember, the answer is, I guess, I don't know. Maybe you can find the answer. Question number 9. This is just calculation. Yeah? Anyone wants to ask something?
Sir, we can find this by finding eigenvalues of A, and
Eigenvalues
then
of A.
yes, sir, eigenvalues of A uh, and the eigenvalues of A transpose are same.
Yeah, but how do you get the
Then
trace of A
multiply.
transpose A?
Then we can multiply.
No, 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 no. This is not the case that I mean, what you are saying is if lambda is an eigenvalue of A for K, suppose, and let's say beta is an eigenvalue of B, then you are saying lambda times beta is an eigenvalue of AB. This is kind of your claim, right? In this example, your B is A transpose.
Or, so we cannot do this, sir, here.
No, we cannot do this. No, this is wrong. This is not true. Eigenvalues are not
Okay,
does
sir.
not behave like this. Just this is keep this as an exercise of finding a matrices A and B for which this does not hold.
Sir,
Yeah.
square of each term of matrix and Then after adding, we get 117. Is 117 is correct answer?
Yes, yes. What you do is you did squares of each entry and then added it, right?
Yeah.
That is
Okay. Yeah.
exactly the what do
Uh,
you say? Diagonal elements of the matrix A transpose
okay.
A.
Hey.
Yes. Okay. The answer is 117. Thank you. I mean, this is another form, but I think sir also defined it in the same way, I guess. Summation Aij squared I or J. This is the way sir defined the norm, right? Norm A is squared.
Yes, sir. Yes, sir.
Yeah, these two are same. Let AB, this is question number 10 now. Last question we had. Surprisingly, we finished so early. AB has recrossed real recrossed symmetric matrix with eigenvalues 1, 2, and 2. If the eigenvector, this has to be eigenvector, corresponding to eigenvalue 1 is this guy, and eigenvectors corresponding to eigenvalue 2 are these two. And what is A square plus B square? Hmm. Anyone have any ideas? See, these kind of questions will be there in competitive exams. GATE, NET, JAM, whatever exams you're preparing for. That's somewhat tricky questions. They can even take your time if you. There are two approaches. You can either go in standard form, you can assume maybe the matrix A as, let's say, because it's real three cross symmetric, you may think, okay, let's do this. And then one by one put all these things, 1, 1, 1 as 2, 2, 2, since it's an eigenvector corresponding to 2, then you get some equation. Similarly, you do it for this 0, 1, 2, you get some equation. Do it for AB1, you get some equation. Solve all those equations and get actually what the matrix A is, and then get an answer. This is one method, but that's so exhausting, you won't get enough time in any competitive exam. Other ways, you have to find some properties of real symmetric matrix regarding their eigenvectors and do this problem. Does anyone remember any good properties of real symmetric real symmetric matrix? Properties of their eigenvectors?
Sir, answer is 5.
Uh, I don't know the answer. How do you
Okay,
get
sir.
the answer directly? Maybe it's 5. I'm interested more in the method. How do you do it? Okay, what are the interesting properties of real symmetric matrix you can think of? Just tell me the properties that you know. We'll see which one we can apply. This is how we think, like you have given a problem, you just search in the data that you have in your mind and then try to apply each one, which one applies. Okay, so the property that we'll use here is eigenvectors corresponding to distinct eigenvalue are orthogonal. This is very important property. That is, now since AB1, see AB1 is an eigenvector corresponding to eigenvalue 1, which implies inner product of A, B, comma 1 with the other two eigenvectors has to be 0. What do you get from here? A plus B plus 1 is 0 and B plus 2 is 0. Simply you get B as minus 2 and you get A minus 2 plus 1 minus 1 is 1. What is A square plus B square? 1 plus 4, it's 5. Yeah, the answer is 5. Surprising. Okay, is it clear to everyone?
Yes, sir.
Yes, sir.
Yeah, and this property, the eigenvectors corresponding to distinct eigenvalues are orthogonal. Is it covered in the course? Did sir explain this property? Proof? Okay, maybe if not, I'll try to cover. Let's see. Transposes in real symmetric matrix or in real matrices, what is the use of transpose? Basically, say inner product of any two vectors x comma y. What is this? This is y transpose x, right? As matrix product, you write y as suppose y1, y2, yn. This is y transpose, and then x is this your vector x1, x2, and then xn. This is your inner product x1, y1, x2, y2 until xn, yn, right? Now, why transposes are important because you get this equality. Inner product of Ax with y is same as inner product of x with A transpose y. Okay, and when you go for adjoints, in real case, adjoints is same as A transpose. You have this equation: inner product of Ax with y is same as x with inner product of A star y. Or maybe in this course, he represents it as AH, something conjugate transpose. Vishnu Priya, you raised your hand. Do you have any question? Okay. So because of real matrices, we can ignore this conjugate transpose case and let's see this one. So now say lambda or let's say x and y are eigenvectors corresponding to eigenvalues what lambda and beta, suppose. These are two distinct eigenvalues and these are corresponding eigenvectors and x and y. What we want to prove that inner product of x with y is 0. Right? That's what it means, that eigenvectors corresponding to distinct eigenvalues are orthogonal. Let's see what is inner product of x with y. Okay, let's say I'll multiply first with lambda. Lambda times inner product of x with y. I can take lambda inside. This is inner product of sorry, lambda x with y. But you know that x is an eigenvector corresponding to eigenvalue lambda. That means this is same as ax. Now, because of the property of transpose, I get this as same as inner product of ax with a transpose y. And then because y is an eigenvector corresponding to eigenvalue, what do you say? No, not just that. We have skew symmetric matrices. No, what do we have? Real symmetric matrices. So A transpose is again A, and now you have y as an eigenvector corresponding to eigenvalue beta. So you get beta y, and beta gets out. what do you have? Lambda inner product of x with y is same as beta conjugate inner product of x with y. That is lambda minus beta bar of inner product of x with y is 0. But since eigenvalues are real, beta bar is same as beta and lambda is not equals to beta, implies this product is 0 only if x y 0. Is it okay?
Yes, sir.
I have used the fact that eigenvalues, real symmetric matrices has only real eigenvalues, and then everything follows. This is a short proof for the fact that eigenvectors corresponding to distinct eigenvalues of real symmetric matrices are orthogonal. Okay, so do you have any doubts in the whole session today? Surprisingly, it finished very early. Haven't seen the whole questions. Otherwise, I would have added more. That they have only 10 questions and they are finished. Do you have any concepts that you want me to discuss? We can discuss the concepts that we have some time left. Anyone can suggest the maybe concepts that you don't understand. You can write it in the chat box and maybe we can discuss those concepts. Okay, if there are no doubts, no suggestions, we are done for today. Maybe in the next session, I'll try to cover more and more problems. But this session, today's session is finished. See you all next week on Tuesday, 6 to 8. Okay, I remind you session is over. So those who don't have any doubts, they can leave. I'll close the session.
Please repeat the last proof you have done.
Last proof, the eigenvectors correspond to distinct
Yes, sir.
eigenvalues.
Orthogonal, yes.
Okay, I will repeat again. See, A, B, real 3 cross 3 symmetric matrix or any, need not be 3 cross 3, n cross n real symmetric matrix. The claim is that eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, so what we do is say x and y, say x be eigenvector corresponding to eigenvalue lambda and y be the eigenvector corresponding to eigenvalue beta. lambda is not equal to beta. So I have distinct eigenvalues and you have corresponding eigenvectors. You want to show that inner product of x with y is 0. So we show that. We will use the fact that now lambda times inner product of x with y, I can take this lambda inside, this will become, now since lambda is an eigenvalue, you have these equations ax equals to lambda x and ay equals to beta y. So this is lambda x, I can replace it by ax, and then I can write this as this by using the transpose properties. Because what is this thing? This is here is y transpose, a transpose, x transpose. No, sorry. This is y transpose ax. What is this? This is a transpose y whole transpose times x. This is same as y transpose ax, right? Basic property. Now, because of symmetricity, what you know is A transpose is same as A. You can write it here A again. Now Y is an eigenvector, so here comes Y. Then beta comes out because it's real. So what you get is lambda times inner product of x with y is same as beta times inner product of x with y. Since lambda is not equals to beta, the only conclusion we'll get is inner product of x with y has to be 0. Because this is a number, right? And you are multiplying the number by two different numbers and you are getting the same result. This happens only if the number is 0.
Yes, sir. Sir, beta matrix is real here, so that's why beta
Yeah,
simply outside
yeah,
from
that's
inner
the reason
product.
beta came as beta. Otherwise, it could have came as beta bar.
Okay, sir.
Yeah, yeah. In the general case, in complex setting, in case of symmetric, we consider the Hermitian matrices. Yeah, but in this case also all eigenvalues are real. Okay, there's a difference. Okay, you should notice in complex matrices also you have symmetric matrices, but those need not have real eigenvalues. But in complex, if you consider the Hermitian matrices, those always have real eigenvalues. Hermitian means A is same as A star usually, but in the course I think they call it as AH, which is complex conjugate. No, no, sorry,
Yes, sir.
complex transpose. Sorry, complex transpose. What is the word? Conjugate transpose. Yeah,
Yes, sir. Conjugate.
yeah. This is conjugate transpose. So because when the eigenvalues, sorry, when the matrices are real, there is no meaning of conjugate, right? A bar is just A when the matrix is real. So it boils down to the symmetric matrices, but the result is actually for Hermitian matrices that all Hermitian matrices have the real eigenvalues and eigenvectors corresponding to distinct eigenvalues of Hermitian matrices are orthogonal. This is the main result. And exactly same proof follows. In place of AH, you replace A transpose or Hermitian. Okay. I hope it's clear.
Okay, sir.
Okay, then I will close the session. We'll see you all
Thank you,
next
sir.
Tuesday. Thank you.
Thank you, sir.
Yeah, thank you. Yes, Vidya, do you have any question?